Hello everyone. Now we will continue our Q&A session, and today's topic is about fluid flow through porous media. Especially it's about steady state flow for incompressible fluid. Okay, so this is our case. An oil well in the nameless field is producing at a stabilized rate of 600 stock tank barrel per day at a stabilized bottom hole flowing pressure of 1800 psi. Analysis of the pressure buildup test data indicates that the pay zone is characterized by a permeability of 120 millidarcies and a uniform thickness of 25 feet. The well drains an area of approximately 40 acres, and the following additional data is available. So we have wellbore radius of 0.25 feet, oil formation volume factor of 1.25 barrels per stock tank barrels, area 40 acres, and oil viscosity of 2.5 centipoise. And we need to calculate the pressure profile or pressure distribution and list the pressure drop across 1 feet intervals from wellbore radius to 1.25 feet, 4 to 5 feet, 90 to 20, 99 to 100 feet, and lastly, 744 and to 745 feet. Okay, so this is the table. And this is our assignment. We need to create the pressure profile plot and list the pressure drop across 1 feet intervals. Okay, so flow rate, bottom hole flowing pressure, permeability, thickness, area, wellbore radius, oil formation volume factor, and oil viscosity. But we need to know the condition of the flow. And here we have information. It says that the flow rate is stabilized and the bottom hole flowing pressure is also stabilized. From here, we can assume, I will say, condition or flow regime based on the information that the rates and the bottom hole flowing pressures are stabilized. So we can assume that the condition is steady state, SS, steady state flow. So we can use equation from steady state flow. And we don't have information regarding the compressibility. So let's just assume that the fluid type is incompressible. Okay. In the case that we have the oil viscosity, maybe we can also assume slightly compressible fluid. But in this case, let's start with the assumption that we can assume the fluid is incompressible and the flow regime is steady state because flow rates and the flowing bottom hole pressure are stabilized. Okay, and this is the concept. Let's say we assume radial flow, steady state, incompressible fluid. So I will add steady state here, steady state. Okay. Steady state flow, radial flow, incompressible fluid. This is the concept, the external pressure, and this is the flowing bottom hole pressure, and then this is the thickness, wellbore radius, and drainage radius. For the case of steady state radial flow of incompressible fluid, we know that the flow rate applicable is in this equation. Okay, and additional information, this is the drainage radius equation if we assume a circular reservoir or a cylindrical reservoir. Okay, so here we start from flow rate equation, but our assignment is to create pressure profile, not flow rate. So we need to rearrange the equation a little bit to get the pressure. So this is the solution. First, we need to rearrange this one. We rearrange to know the pressure and to solve for the pressure at radius r, at certain radius. And if we rearrange the equation, we will get this equation to get the pressure. So pressure at any location R is flowing bottom hole pressure plus this term multiplied by logarithmic natural of R divided by RW. So first we will create equation. And the equation is like this. First, we need to calculate this one, this term. We know that the PWF is 1,800 here. All right, and then we will borrow the viscosity and oil formation volume factor. Okay, copy and paste here. And also the flow rate. I will take the number and wellbore radius, RW. All right. So first I will calculate this one, this term. Let's say, yeah, I will just calculate. So this term is actually viscosity multiplied by oil formation volume factor multiplied by flow rate 600 divided by 0.00708 multiplied by, oh, we forget this one, permeability multiplied by thickness, and I will close the parenthesis. Okay, so this term is 88.28. Okay. All right. So now we can get the calculation or the equation. It is P equals to, all right, P equals to, what is the PWF? PWF is 1,800. All right. And then it will plus like this, plus here it is 88.28. All right. And then multiplied by logarithmic natural of R divided by RW, which is 0.25. And let's say I will make a table for this equation. I will make a box. Okay, so this is our new equation. So pressure at any location is 1,800 plus 88.28 multiplied by logarithmic natural of R divided by 0.25. So now the next step is we will create the pressure distribution or pressure profile. And we start from wellbore radius, 0.25, and then plus 1 feet, because here it says that we need to create pressure profile and list the pressure profile pressure drop across 1 feet interval. So this one plus 1, okay, 1.25, and then for 5, right? 4, 5, 19, 20, 99, 100, 744, and 745. 19, 20, 99, 100, 744, and 745. Okay, let's make them bigger. Okay, actually this one, 745 is RE. Okay, just to make sure, this one, SQRT square root of 40,560 multiplied by area divided by P. All right, but it is, I think, acres, maybe, if I'm not mistaken. Yeah, I'm not sure. I need to convert the area first. Let's say this is acre, right? 40 acres. So 40 in acres. I will first convert it to meter squared or maybe feet squared. Okay, can we do that? Convert 40 from, let's find acres. Yeah, you can convert the unit using this function in Excel. Okay, acres, I think this one, US acre. This one, US acre. Okay, change it to feet square foot, I mean. Okay, so this one, and then let's find the drainage radius. It's square root, SQRT, of 40,560 multiplied by the area, which is this one in square foot, divided by P. Okay, this is square root. All right. And then I will make this like this. Okay, let's make sure square root or we need to make sure about this. All right. Or maybe this one should be multiplied by this one divided by P. All right. So a mistake previously. So A here, it's already acre, and 43,560 is actually unit conversion. Okay, so if we apply this equation, the drainage radius RE is actually already in feet. Okay, so this one, right, is 745 feet is actually the drainage radius. Okay, so RW 0.25, drainage radius 745. And yeah, we can calculate the pressure, okay, using this equation. So it is 1,800 plus this one, 88.28, make this dollar, okay, F4 to lock this number. And maybe I can use also this one, bottom hole flowing pressure, log the number, and then multiplied by logarithmic natural ln of the radius divided by wellbore radius, this one, and then I press F4 to lock this value. Okay, starting from 1800, and then I will just drag the calculation like this. And yeah, I get the profile, pressure profile. Now let's say I want to make just a radius interval as per the assignment. Okay, because we are asked to list the pressure drop across 1 feet intervals. So I will make this 1 feet, and then merge like this interval 1 feet, 1 feet, 1 feet, and 1 feet. Okay. And then format cells. Okay. And then this one is 0.25 to 1.25. This one is 425, 425. This one is 19 to 20. This one is 99 to 100. This one is 744 to 745. And then just the pressure drop. Pressure drop, it is in PSI. Okay, I will make also the merge like this, delete, and then let's calculate the pressure drop. This one is this one minus 1800. So the pressure drop across 1 feet interval is 142. This one, this minus 2045. So now from this location to 5 feet, 4 to 5 feet, only 1 feet interval, pressure drop 20. It's very different from this one. 1 feet interval, but the pressure drop is 142. It's very big, the pressure drop here. So I will highlight this number. And then at 19 to 20 feet, let's calculate the pressure drop. Now it's even smaller, 5. And then this one to this one, it's even smaller. And lastly, I will expand the number. Now the pressure drop is very small across 1 feet interval. It's now only 0.1 psi. So the biggest pressure drop occurs here, close to the wellbore radius. Wellbore radius is at 0.25, 1 feet interval. Here, the pressure drop is very big. Yeah, that's the characteristic of radial flow. As you go closer to and closer to the wellbore, the pressure drop becomes bigger and bigger, greater and greater. And let's say we want to create a plot out of this table. Okay, I will create a plot. This is my plot. Select data, add series name. I will call it pressure profile. X-axis here, the radius, and the vertical axis, y-axis is pressure. So it's like this. And I want to make line, format data series, solid line, I will make the fill maybe yellow, the border red. Okay, so this is our plot. I will also make axis title. So this one is radius in feet, and this one is pressure P in PSI. There you go. All right. So you see the pressure profile is like this, and closer to the wellbore, the pressure drop becomes more significant. If I maximize at this point, at this location, so I will format axis 100, and then let's say we start from 1500. You see, after I zoom in, the pressure drop at this location is at the greatest. All right. Again, just 1 feet interval, the pressure drop is 142. If we make it even bigger, all right, zoom in, it's like this. All right, so this is the case for steady state flow, radial flow, for incompressible fluid. Okay, so that's all. I hope you enjoyed the video. I hope the video is useful. Thank you so much for watching, and see you again in the next Q&A videos. Thank you.